First, I would like to thank Professor Breed and Bianco for their kind invitation. It's a great chance for me to share with you some results we got in the last year regarding the possible application of an integrated approach based on exercise and nutrition and metabolic disorders. The title of my talk is Route for the Application of Exercise and Nutrition Integrated Approach in Metabolic Diseases, and deals with a disease called carnitine palmitoyltransferase 2 deficiency, a very rare disease that is considered by us a prototype to apply exercise and nutrition approach in metabolic disorders. Results from our study is published in a recently published paper in Frontiers Physiology. And this work has the idea to propose a new theoretical basis for potential application of exercise, nutrition, and also supplements in metabolic diseases, and in particular in this disorder, the CPTII deficiency, 50 years after the discovery of this pathology. So to understand what I'm talking about, I should go through the role of rhabdomyolysis in metabolic disorders. Rhabdomyolysis is a classical presentation that we can find in almost 50% of rhabdomyolytic patients in the childhood and in higher percentage in the adult. This classical presentation includes myoglobinuria with dark urine, muscle weakness, and muscle cramps. So, but what is rhabdomyolysis? Rhabdomyolysis consists in the partial and abrupt ruptures of the sarcolemma, followed by dramatic increase of several molecules normally contained within the cells, including CK, creatine kinase, lactate dehydrogenase, LDH, myoglobin. And all these molecules first reach the extracellular space and then the bloodstream. The molecules are used as biomarker, clinical biomarker of the disease. Normally, the CK levels in the bloodstream ranges between 22 to 200 unit liters. In case of rhabdomyolysis, these values goes up to 10,000 to 200,000 unit liters. And this happens 24-48 hours after the event, that generally is triggered by prolonged exercise. Apart the clinical presentation of the rhabdomyolysis, to go through the causes of rhabdomyolysis, we should perform several exams, including also sometimes electrocardiograms and muscle biopsy. The mechanism behind rhabdomyolysis deals with protease activation through an increase in calcium within the cells. This increase is followed by ATP reduction and reduced activity of the sodium-potassium ATPase, increased activity of the sodium-calcium exchanger, and so activation of protease and membrane destruction. The calcium overload within the cells is followed by oxidative stress, ROS production, reactive oxygen species that damage directly the nucleus and the mitochondria. So the triad in these cases include mitochondrial damage, apoptosis, and muscle destruction. After the muscle destruction, myoglobin and the enzymes are released into the circulation and damage the capillaries. This leaking to fluids into interstitium and causing edema. Hypovolemia then arises and decrease the renal blood flow. This, in combination with myoglobin toxicity, causes an acute kidney injury. So, in rhabdomyolysis, we have several complications, including acute kidney injury, the possibility of hypovolemia, the possibility of alteration in electrolytes, including hypocalcemia, hyperphosphatemia, hyperkalemia. And in the late stage, we can assist, we can see disseminated intravascular coagulation and hypercalcemia. So complications of rhabdomyolysis can be very important from a clinical point of view. The rhabdomyolysis is caused by two groups of causes. From one side, we have acquired causes, including traumas, exertion, in particular prolonged exercise, with energy depletion and electrolyte imbalance, ischemia, the use of certain drugs, infections, the exposure to extreme temperature, including cold, hypothermia, or hot environments, and also some diseases of the endocrine system, including hypothyroidism and complications of diabetes. The inherited forms of rhabdomyolysis include metabolic myopathies, and among them, myopathies of the glycogen storage or fatty acid utilization of mitochondrial disorders. We can have rhabdomyolysis also in dystrophic conditions, including those that cause alterations of the dystrophin glycoprotein complex and some other inherited conditions, including channelopathies, so mutation in genes that code for channels. So the main causes of rhabdomyolysis from the inherited forms include disorders of glycogenolysis, in particular myocardial disease, disorders of the lipid metabolism, in particular the carnitine palmitoyltransferase deficiency and the long-chain acetyl-CoA dehydrogenase deficiency we are dealing with in this talk. So what about lipids? We know that lipids are essential for structural and functional maintenance of muscle cells. The fatty acids are basic molecules that play an essential role for energy production in skeletal muscle, cardiac muscle, and in particular during prolonged exercise. The acute lipid oversupply shifts glucose utilization, and the mitochondria in this condition preferentially switch from carbohydrate to fatty acid utilization. This explains that the cell has a high degree of metabolic flexibility, particularly in skeletal muscle. The variation in fatty acid entrance within the cell is able to modulate the fatty acid oxidation rate. So the utilization of fatty acids within the cells is driven by four principal steps that are shown in this figure. The first step is the entrance of fatty acids within the cytoplasm through proteins at the sarcoplasmic membrane. The second step is storage or breakdown of the lipids in form of droplets of fatty acids. Third step is the transportation of fatty acids within mitochondria from the external to internal mitochondrial membrane. The fourth step is the releasing the mitochondrial matrix and utilization through the beta oxidation. Carnitine protein is mainly responsible for fatty acid entrance through the cell membrane. The fatty acids are stored in the cytoplasm as triglycerides and lipid droplets, and they can be hydrolyzed by a subset of lipases. This is followed by the entrance of fatty acid in the mitochondria, thanks to the action of four components, in particular the carnitine palmitoyltransferase 1, mitochondrial trifunctional protein, the carnitine acetylcarnitine translocase, and the carnitine palmitoyltransferase 2. Then fatty acids are metabolized by the electron sulfate flavoprotein and beta oxidation enzymes. Of course, any change in these different steps can cause a defect in the lipid utilization by the cells. and it can cause cellular imbalance that may lead to rhabdomyolysis through the calcium overload within the cells. This is actually sometimes followed by atrophy, myalgias, myoglobinuria. So to summarize, four components are particularly important for fatty acid entry within the mitochondria, in particular CPT1, NTP, CACT, and CPT2. To summarize the process, we have the acyl activation. In this case, the long-chain fatty acids reacts with the molecule of CoA. This needs the consumption of the ATP, and by the enzyme acyl-CoA synthetase, which is found in the outer membrane of the mitochondria. This process is followed by the generation of molecules, acyl-CoA. The long-chain acyl-CoA enter the outer mitochondrial membrane through the carnitine shuttle. The molecules are then conjugated to carnitine by CPT1. The translocate transport the acetylcarnitine across the inner membrane of the organelle. In fact, this membrane is highly permeable, and only few molecules can reach the mitochondrial matrix by diffuse simple diffusion. CPT2 therefore release the acyl-CoA and transport the carnitine back into the cytoplasm. So the CPT2 deficiency is a disease we are dealing with in this research. This is the most common disorder of lipid metabolism affecting the skeletal muscle with a unknown prevalence and an autosomal recessive inheritance. In the myopathic form of the CPT2 deficiency, we have a missense mutation in the CPT2 gene, and in the Caucasian population, we have a most frequent mutation in P113 The disorder affects the mitochondrial oxidation of the long-chain fatty acid and is known as the least severe form of CPT2 deficiency, being the most severe mortal and deadly disease in the younghood. What characterizes deficiency CPT2 are recurrent bouts of rhabdomyolysis following prolonged exercise, and is frequently aggravated by extreme temperature or prolonged fasting. The episodes of rhabdomyolysis are associated with an abrupt increase in creatine phosphokinase and myoglobinuria, and in 25% of the cases we have a kidney injury, but rarely this leads to dialysis. Differential diagnosis is based on myocardial disease, DMD, and cytochrome C oxidase deficiency. Notwithstanding the inherited disorder, the defective fatty acid transportation into the mitochondria regards only a part of the bulk of long-chain fatty acid available, and reduction is about 15 to 50% compared to normal values. So a certain degree of fatty acid oxidation is still occurs. From a clinical point of view, it's very interesting that in the intercritical period, the CK into the blood is normal in these patients, whereas in the critical period, we can assist to and we can see an abrupt increase in CK in the blood. Normally, during the intercritical period, the subject is almost healthy, whereas during the critical period, we can see symptoms related to sarcolemmal damage and disruption, myalgias, cramps, and muscle weakness. So the current recommendations for CPT2 deficiency are mainly aimed at reducing the severity of disease symptoms, and this recommendation include rest and the assumption of high percentage of carbohydrates in the diet. But this approach does not take into the proper account that the long-term consequences of an approach based on the disuse and on high percentage of sugars into the diet, and how they can impact on the subject's health in the long run. In this scheme is summarized what is generally suggested to the patients. A diet, a calorie intake based on 70 to 80% of carbohydrates, but always more than 70%, 15% of fats, 15 to 20% of proteins. So the diet is highly unbalanced towards carbohydrate utilization. So which are the intersections we propose between exercise and nutrition to promote health maintenance in these patients, and to consider CPTII deficiency as a prototype to study other metabolic disorders, in particular lipid disorders. First of all, we propose no rest because we believe on the role of intermittent training and resistance exercise in this disease. We all know that the energy sources are differently used according to duration of the exercise and intensity of the exercise. If we consider a very short time exercise at high intensity, we believe that the fat utilization in this condition is the lowest possible. Being the energy sources mostly utilized within the cells, the creatine phosphate system, phosphagen system, and the anaerobic glycolysis. Following longer exercise, the aerobic oxidation and mitochondria start to arise and to represent the major fuel source within the cell. Another aspect that we should take into consideration is the possible crosstalk between mitochondria and peroxisome in the skeletal muscle cells. Recently, strong evidence supports a close relationship between these two organelles within the muscle cells, in particular regarding the process of oxidation of fatty acids. Beta oxidation occurs both in the mitochondria and the peroxisome, but involves different substrates. In particular, short, medium, and long chain fatty acids are oxidized in the mitochondria, whereas very long chain fatty acids are mainly oxidized in the peroxisome. Other substrates include the carboxylic acids and branched chain fatty acids, which are typically oxidized in this organelle. Mitochondrial and peroxisomal beta oxidation also lead to the formation of end products which are slightly different. In particular, in the first case, acetyl-CoAse is produced and afterwards directly processed by the tricarboxylic acid cycle. In the second case, beside acetyl-CoA, other acyl-CoAs are produced and convert in carnitine molecules by carnitine octanoyl transferase, COT, and carnitine acetyltransferase, CAT. Then transport in the inner membrane of the mitochondria through carnitine acetylcarnitine translocase, CACT, and then reconverted to acyl-CoA by CAT before reaching the final destination, that is the mitochondrial beta oxidation or the tricarboxylic acid cycle. So a possible crosstalk between these two organelles may sustain beta oxidation also in the presence of carnitine palmitoyl transferase 2 deficiency. Another aspect that should be taken into account is the nutritional approach in these patients. In particular, is the high carbohydrates diet the right way to counteract progression of the disease? In particular, we all know that high carbohydrates-rich diet produces an hyperglycemic stimulus and a hyperinsulinemic response. This reduces the muscle fatty acid oxidation, at least in humans, and hyperglycemia and hyperinsulinemia functionally reduce the activity of CPTII in muscle cells. Indeed, production of malonyl-CoA following greater availability of glucose has an inhibitory action on CPT2. So, we propose another approach based on lower carbohydrates intake of about 50 to 55%, higher increase in fats to 20%, which is the minimum level to maintain HDL production within the cells, and higher proteins intake to counteract disuse and the effect of disuse on skeletal muscles in these patients. All this theory was applied in the case of carnitine palmitoyl transferase 2 deficiency. In particular, it was a young girl that was analyzed in our laboratory. She had a long story of hyper-CKs and rhabdomyolysis with hospitalization, followed by a series of exams that allowed at the end to establish the presence of CPT2 deficiency. In particular, she had a biopsy, a resonance. She had some biochemical examinations to exclude Pompe disease and McArdle disease. And she was also evaluated for genetic analysis for identification of DMD, the Duchenne muscular dystrophy, which was negative. And again, a neuromotor evaluation with 6 minutes walking test, again negative. In this girl, after the diagnosis, genetic diagnosis of CPT2 deficiency, we propose an exercise training based on two different kinds of approaches. One was an endurance exercise, in particular, an interval training consisting in a 1 minute run and 5 minutes walk for 15 minutes, progressively increased to 30 minutes, 3 times a week for 6 months. And again, a resistance exercise training based on 3 sets of 8 repetition with 2 minutes rest between sets. In this case, we were focusing on the rapidity and speed of executions of the repetitions to avoid the utilization of fatty acid substrates in cells. The training consists in upper body exercises, including bench press, shoulder press, lat pull down, dumbbell flies, and dumbbell pull over and arm curls. And during the training, lower and upper split workouts were carried out. The load was fixed at 6 to 7 of the 0-10 scale for resistance exercise according to Robertson 2003. All the results were positive, and she didn't experience any episode of rhabdomyolysis during the 6 months training. In particular, I would like to focus on a parameter that is the respiratory quotient, that at the beginning of training was 1, and at the end of training was 0.85. All of us know that this parameter is the mirror of macronutrients utilization at rest. So she had a metabolic improvement during and after training. This was also demonstrated by increased workload and heart rate max during CPET experiments, and by a significant increase on the period of isocapnic compensation during the test. Similar results were obtained parallelly by a different group in Spain, in particular by the Santalla group, in a case of very long-chain acetyl-CoA dehydrogenase deficiency. In this, this enzyme is the enzyme that catalyzes the first and limiting step of beta oxidation of fatty acids, in particular long-chain fatty acids, from 14 to 20 carbon atoms. The deficiency of this enzyme is the second major metabolic disease involving utilization of fatty acids and muscle cells. There are three phenotypes of the disease. One is very severe, it's a cardiomyopathic form. The other one is mild. The third is myopathic form, and Santalla's group was dealing with this one. In this slide, they propose the difference between a normal subject and a subject carrying a VLCAD-M disease regarding fat oxidation capacity. As described in the figure, a much less capacity of fat oxidation is present in these subjects, but exercising at high intensity with high intensity interval training avoid the risk to fall into the load interval where fat mass is present in the person, in the patients. So they propose a training of 6 months. This time was supervised. The exercise combined two kinds of different approaches in HIIT and strength training. The first month, they had only HIIT. In the following 5, there was a combined training. HIIT was done in a cycle ergometer and was 6 sets of 7 to 80 seconds, performed at maximum intensity with a cadence of 100 RPM and 1 passive recovery period between sets. These were the training for strength training, including bench press, bicep curl, bent over, dumbbell row, line traps and extension, dumbbell lateral rise, half squat using body weight. So also in this case, they observed a significant improvement in metabolic and functional parameters recorded with CPET in the patient. And they also observed increase in VO2 peak and heart rate max and power output at the end of treatment. So to summarize, our innovative potential treatment for CPTII deficiency patients and in general in subjects carrying metabolic disorders of lipids, we propose a dietetic approach based on higher proteins, 25 to 30%, lower carbohydrates than those generally suggested, 20% of fats. Whereas the exercise suggested is a personalized exercise program combining HIIT or MIIT at 70% VO2 max, resistance training. Whereas the exercise to be avoided is the traditional endurance activities like running, cycling, swimming at a percentage of V2O max less than 65%. And this should be avoided in CPTII and VLCAD-M patients. The lifestyle to be maintained is physical activity, and inactivity and disuse should be discouraged in these patients that very often experience an increase of body weight and fat mass due to combined disuse and very rich diet in carbohydrates. So I have no time to go into the supplementation that we suggest in these conditions, but I would like to thank you all for the attention, the possibility to share these results, and I hope that the conference held by Patrick Drake and all the team and Antonino Bianco will have a great success in the meantime. So thank you for your attention and see you soon.